Have you ever stopped to think about what the world around you is actually made of? I mean, really made of. From the phone in your hand to the clothes on your back, there's this secret ingredient everywhere: polymers. We're so used to them, we barely even see them anymore. But what are they? In this explainer, we're going to pull back the curtain on these giant molecules and see why they're both a modern miracle and a massive challenge. Okay, check this out. If you've ever seen the incredible waterfall at Jewel Changi Airport, you've witnessed a polymer doing something spectacular. That massive funnel guiding the water is enclosed by acrylic. Yeah, acrylic. It's this super strong, totally transparent polymer. It just goes to show you these materials aren't just for flimsy plastic bags. They're architectural wonders hiding in plain sight. So here's our game plan for today. First up, we'll get to know what these giant molecules are all about. Then we'll put on our chemist hats and figure out the two main ways to build them. And finally, we're going to face the music and ask the big question: what on earth do we do with all this plastic once we're done with it? All right, let's dive right in. Section 1, our world of polymers. Time to get down to the basics. So what is a polymer? At its heart, it's actually pretty simple. The name itself is a clue. Poly means many, and mer means parts. So many parts. And the Lego analogy here is perfect. Think of a single, small Lego brick. In chemistry, we call that a monomer. Now, when you click thousands of those bricks together to build something big, that final creation is the polymer. That's it. And here's what that looks like. On the left, you've got that single monomer, our one Lego brick. Then, through a process called polymerization, thousands of them link up with these really strong covalent bonds, and you get that long, massive chain on the right. That's your polymer. It's that simple, from one unit to a massive chain. And get this, it's not just something we humans invented. Nope, nature has been the master polymer maker for millions of years. Things like wool, the silk from a cocoon, even the starch in your food, all natural polymers. We just got smart and figured out how to cook up our own synthetic versions, like the nylon and PVC you see here, for everything from workout clothes to water pipes. So, how do we actually make them? What's the recipe? Well, method number 1 is called addition polymerization, and the name tells you pretty much everything you need to know. It's all about, well, adding up. Here's the key idea. In addition polymerization, you start with special monomers that are called unsaturated. All that means is that they have a carbon-carbon double bond. That double bond is key because it can break open, allowing the monomers to link up one after another into a long chain. And the best part? Nothing is lost. Not a single atom. It's pure, clean addition. You've definitely seen this in action. That plastic bag from the grocery store, it's made of polyethylene, a classic example of an addition polymer. You've literally handled this exact chemistry hundreds, maybe thousands of times, probably without even thinking about it. So how does it happen? It's basically a 3-step dance. Step 1, you take a bunch of ethene monomers. Step 2, you apply some serious heat and pressure, and that makes their double bonds pop open. And finally, step 3, they all link up, hand in hand, to form one long continuous chain of polyethylene. Simple as that. Nothing created, nothing lost, just one big chain. All right, let's hit pause for a quick brain workout. This is called retrieval practice, and it's scientifically proven to help you remember stuff way better. So we've gone from the small brick to the big structure. Can you do it in reverse? If I gave you the final polymer, could you figure out what the starting monomer was? Go on, give it a shot. So, did you figure it out? It's like being a chemical detective. First, you just scan along the polymer chain and find the bit that repeats over and over again. That's your repeating unit. Step 2, you isolate it. And for the final trick, you just turn that carbon-carbon single bond back into a double bond. And ta-da! You've found your original monomer. Awesome. Now, let's move on to our second recipe: condensation polymerization. The big clue is in the name here too. But this time, when the monomers join up, something gets left behind. You might actually be wearing a condensation polymer right now. Go ahead, check the label on your shirt. If it says polyester, you're wearing one. Fabrics like terylene and nylon are made this way, and this specific process is what makes them so incredibly strong and durable. Okay, so here are the two big differences. First, you often use two different kinds of monomers. And second, when they join together, a small molecule, usually water, gets kicked out. It's like the monomers are condensing together and squeezing out a tiny water droplet every time they form a link. Let's look at how nylon is made. You start with two different monomers. The ends of these molecules are designed to react with each other. A piece from one monomer grabs a piece from the other, they form a water molecule, and that water molecule is eliminated. It's gone. The parts that are left behind then snap together to form a super strong bond called an amide linkage. You do that thousands of times and you get nylon. Okay, let's put it all together side by side. This is the crucial bit to remember. For addition, you use unsaturated monomers, and there is no byproduct. For condensation, you use monomers with two functional groups, and you always get a small byproduct, like water. If you can remember those two key differences, you've totally got this. We've seen how we make these incredible, versatile materials. But there's a flip side. What happens when we're done with them? And that brings us to the really big, really tough part of the story, the plastic problem. Here's the core issue in a nutshell. The very thing that makes plastics so amazing, their strength, their durability, the fact that they don't rust or rot, is also their biggest flaw. They are non-biodegradable. That means nature can't break them down. So, pretty much every single piece of plastic ever made, unless it's been burned, is still out there somewhere. And the result of that is, well, you can see it right here. This waste piles up in our landfills and tragically finds its way into our oceans, harming wildlife and ecosystems. It's a huge paradox, right? The incredible chemical stability we designed into them is the very thing that makes them such a persistent problem for the planet. Now, get ready for this number. It's a bit of a shocker. Looking at data from Singapore in 2019, only 4% of the plastic waste from households was actually recycled. Just 4%. That means 96% wasn't. So why is that number so incredibly low? Well, the hard truth is that recycling plastic is a real headache. It's not as simple as just tossing it in a blue bin. There are big economic hurdles. It's often more expensive to recycle plastic than to just make brand new plastic from oil. There are technical problems. Just a little bit of food waste can contaminate an entire batch and make it useless. And then there's the human factor. It just takes a lot of effort to get everyone into the habit of recycling properly. This mind map here really pulls our whole story together nicely. Let's trace it. We start at the top with polymers, which are built from monomers. We use polymerization to create plastics, which have tons of great uses. But if you follow that branch down, you hit the consequence: pollution. And right now, the only escape route from that is recycling, which, as we've just seen, is complicated. But here's the cool part. The story of polymers is far from over. Right now, scientists are designing incredible new smart polymers that can do things like conduct electricity or even heal themselves when they get cut. The possibilities are endless. So I'll leave you with a question to think about. Now that you know the rules, if you could invent one brand new polymer, what world-changing problem would you solve with it?